The 5-number summary of a distribution is the list of the min, Q1, median, Q3, and max. And a box plot does all of those things. So if we know the 5-number summary, so for example, on that last problem that we did, the minimum value was 12. Q1 was 66, median was 76, Q3 was 88, and the max test score was 100 on that data set that we had earlier that we were calculating all those things. So if we were writing this as the 5-number summary, we would just write 12, 66, 76, 88, and 100. A box plot is going to 30, 40, 50, 60, 70, 80, 90, 100. My tick marks aren't great, but if we are trying to do a box plot here, I can just start at the minimum value, go up until 66, 76, 88, and 100. I make a box extending from Q1 to Q3, and then I draw a line where 76 was because that's the median. And that's a box plot. So it's pretty straightforward. Typically, we have outliers marked separately. So let's say that 12 was an outlier, and I know we haven't learned how to calculate this yet, but let's say that 12 was an outlier. If we knew that 12 was an outlier and that was the only outlier, and then 37, let's say that wasn't an outlier, then we would start our graph at 37, go all the way to here, and then just mark 12 with a dot. If we had more than one outlier, let's say that 37 was an outlier, then the next data point was 51. So we would mark 37 with a dot, and then we would start the box and whisker at 51 and then continue it. So it just depends on where the outliers are. We typically mark outliers with a dot. Okay, so that's what a box plot looks like. The length of the box is the IQR, and the length of the entire plot is the range. And like I said, outliers are typically marked separately. To determine if there are outliers, we place boundaries around the main part of the data. So let's now actually count and see whether we have any outliers here. So what I know is I know that I calculated the IQR to be 22. So what I do is I fence the data and say Q1 and Q3, and then I take 1.5 times the IQR, which in this case is 22, and say 33 away from either part of the interquartile range is too far away for me to consider that to be a normal observation. So we call that an extreme outlier or an extreme observation or an outlier. Okay, so if I'm looking at this, 33 is the furthest away from the Q1 and Q3 that we're going to consider to be normal. So Q1 minus 33, since Q1 was 66, that means that 33 is the absolute furthest away that something can be before we consider that to be an outlier. So notice that 33 is about here. So 37 is actually not considered to be an outlier. So that means 12 is an outlier on the low side. Now if I do Q3 plus 1.5 times the IQR, that's 88 plus 33. So that would be 121. And no test scores were above 121. So that means we have no upper outliers in this problem. So if I'm graphing the box plot, I know that I can graph the box plot for that test score problem to look like this because there was only one outlier. So then I would stop the whisker at 37 because that's the most extreme observation that isn't an outlier. So this is kind of what the graph would look like of the test score example. Box plots are nice because we can quickly identify the center, spread, and we can typically tell symmetry because wherever the line is in the middle of the box plot, that kind of tells me whether it's symmetrical or not. So if the line was moved further over, that means that I can assume that the graph is probably skewed because my middle value is not in my median is not actually in the middle of my box. And so that can kind of give me an idea of where the skewness lies. When a distribution is skewed, we definitely want to use median and IQR. But if it's roughly symmetric, we can use the mean, so we can add them all up and divide by n. We use x bar to represent the mean of a sample. And then we use mu, which is a Greek letter, to refer to the mean of a population. It's very hard to actually find the mean of a population unless you take a census or your population is pretty small. So we typically do x bar in this case. Graphically, the mean is located at the balancing point. So let's go back to here. If I were trying to balance any of these graphs with my finger, the mean is going to be at the spot where that would actually balance on my finger, basically. So that's kind of what happens with the mean. You also would probably call that the centroid if you were in geometry. So is the mean a resistant measure of center? We already talked about that with the Michael Jordan example. So the answer is it is not a resistant measure, and it is pulled in the direction of the skew or the outlier. Another way to measure the spread of a distribution is the standard deviation. So let's calculate standard deviation. And standard deviation is not something that's all that fun to calculate because it takes a lot of work. So basically, in order to calculate the standard deviation, what you have to do is you have to find the mean. And so what we're going to do is we're going to find the mean of this distribution. So 14, 25, 26, 31, 40, plus 11 is 51, 62, 70. So I have 70 is the total. And then I divide by 10 and I get 7. And that's our mean, essentially. So now what I want to do is I want to find the difference between each observation and the mean and then square it. And then I'm going to divide by 10 minus 1. And the reason why when we're finding a sample standard deviation, we divide by n minus 1 is it accounts for some variability in the fact that we don't know every single observation. So it's going to be, this is my formula for calculating the standard deviation. So it's the square root of the sum. That's what that sigma thing means, the little thing that looks like an E. That means add them all up. So what we're going to do is we're going to take each data point and subtract it from 7. So 1 minus 7 is negative 6. 13 minus 7 is 6. So let's just quickly do that. 6 squared is 36, plus 36, plus 16, plus 36, plus 4. So what the standard deviation of 4.13 means is that we have a typical player, a mean number of home runs for a player is 7, but that doesn't mean that all the players have 7 home runs or anything. So the standard deviation, basically what that is telling us is that while a mean number of home runs is 7, the typical player tends to have 4 or so more or so less home runs than the average. So while 7 is the mean, we could expect normal players to have either 11 or 3 home runs, so to speak. So this is basically telling us that the variation in number of home runs is pretty significant. A lot of people are not going to be around 7. There are going to be some that are around 7, but there are going to be some highs and lows. And that's what the standard deviation is telling us. Um, we know that the standard deviations square, the square of the standard deviation is called the variance. That's basically just not taking the square root there. And if the last value was 41 instead of 11, we can just very quickly kind of figure out what's happening. Instead of that number being a 16, this wouldn't be 4 anymore. This would be 34. And then if we square 34, this number is going to be over 1,000. I mean, more than 1,000, which means that this number is going to go way up. And so an outlier has a very significant effect on the standard deviation. It's not a resistant measure of spread. Just changing that one thing is going to make the standard deviation go way up. Standard deviation is ruler. So suppose that a professional soccer team has money to sign one additional player, and they're going to add either a goalie or a forward. We want to figure out if the goalie is better compared to the league goalies than the forward is compared to league forwards, because it's hard to compare goalies and forwards in soccer. They have very different job responsibilities, and so you kind of have to figure out who's better compared to the other people that you should be comparing them against. So notice that an average goalie saves 86% of shots, standard deviation of 5%. Average forward gets 9/10 of a goal per game with a standard deviation of 0.2. Who's better at their position? So the goalie is 4% higher than average, and the forward is 0.3 goals higher than average. But we can't just say 4 is greater than 0.3 because they're not in the same units. They don't really mean the same thing. There are lots of different ways that we can kind of figure out who's better. Just looking at this numerically may not be the best way to go about it. So we have to change these to compare things that don't have units. So the way we do that is by using a z-score. So z is equal to the observation minus the average over the standard deviation. Okay, so if we were writing this for the entire population, that would be x minus the mean over sigma, the standard deviation. So that would be for the entire population. This is if we have statistics or sample statistics. So if we look at this and we calculate z-scores, the forward is better at goal scoring compared to the league than the goalie is at saving shots compared to the league. So that's kind of important. So the forward is a better goal scorer than the goalie is a goal saver. And so the forward, at least comparing these two statistics, the forward is better than the goalie, even though the goalie's quote unquote number was higher. When using the standard deviation as a ruler to determine how far something is above or below the mean, we call it a standardized score or a z-score. Using standardized scores have many advantages because they don't have any units. So basically, we're just comparing how good they are compared to other people that are doing similar things or other observations that are in a similar format. So we can compare things from different populations that aren't necessarily related to each other, and we can talk about whether something is higher or lower compared to average and compared to how spread out things are. So let's say male heights have a mean of 69 inches and a standard deviation of 3, and female heights have a mean of 64 and a standard deviation of 2.5. Who's taller, relatively speaking? 65-inch male or 60-inch female? Now notice that they are both shorter than average, so we should get negative z-scores because we're having people that are less than the mean, so it's going to be a certain number of standard deviations below the mean. So the male would be 65 minus 69 over 3, which is negative 4/3 which is about negative 1.333. So that means this male is about 1 1/3 standard deviations below the mean. That's pretty far below the mean. Now, the female has 60 inches, so she's exactly the same amount of inches less than the average as the male was less than the male average. So the standard deviation of female heights is 2.5. So we have -4 over 2.5. If I want to multiply the top and bottom by 2, I get a nicer fraction. So that's -8/5, which is the same thing as -1.4. So the female is 1.4 standard deviations below the mean. So who is taller relatively speaking? The male is taller relatively speaking because the male is fewer standard deviations below the mean than the female is. An exclusive club allows only members who are especially tall in it. The height requirement for women is 72 inches. What would be the equivalent requirement for men? So, in order to be in the club, you have to be 72 inches for a female, and the mean is 64. So remember, it's observation minus average over standard deviation. So observation is 72, average is 64, 2.5 is the standard deviation. So that's 16 over 5, which is 3.2. So you have to be 3.2 standard deviations above the mean. So let's now solve an algebra problem. So the z-score equivalently for men needs to be 3.2 because we need to compare them and we want them to be equal. So 3.2 is equal to the observation, that's what we're trying to find, minus the mean over the standard deviation. I know that I can actually find the mean and standard deviation here because I was given them. So the mean height for males is 69 inches. The standard deviation for males was 3. So now what I do is I solve the equation. So I multiply both sides by 3. I get 9.6 equals x minus 69. And then I multiply, or I add 69 over to the other side, and that's 78.6 inches. So that's about 6 foot 6 3/5. 6 foot 6 3/5 inches for a male to be in the Tall People Club.